Like there's kids, people with VR glasses.
Oh yeah.
Yeah.
Yeah, the lobby's huge. You can actually, I've heard they do like weddings in there and other
Oh, yeah.
exciting events in there. You can rent it out.
Wow. That would be a cool place to do a wedding.
Yeah.
Man, I gotta check this out.
Okay, cool. So we're live. So
We are?
you can wave to people in internet.
How many do we have?
We just started, so
Okay.
maybe a couple times or so. No pressure. Actually, some people asked about you know the if we're gonna do like their live and stuff. So I will post it and I will tweet it.
Okay.
We're live. I will post this. And I think you probably wanna can switch back and forth to your presentation.
Yep.
Works well. Alright, so we have just a couple seconds delay, which is perfect in terms of, if something goes really bad here. For some reasons I see a screen. Can you do, disable this presenter view? You just need to just close this. This grabs your screen, but not
Right.
another one.
Yeah, I'm just gonna do it.
No. You just go to present. Click present.
Yep.
So and the close. No. There should be something like use slideshow. No. There we go. So you both have,
Yep.
perfect. So what is perfect. So here it shows us on the screen. I think do like this, and after that we will switch to demo. Can you try it start over? Because on my screen it shows not very nice.
Okay.
Just okay, try again. Just or otherwise you just can have the slide just a little bigger. Yeah.
Yeah, that works too.
Now still switch to this one. Use the slideshow. Nah. Just do it. Yeah. Just do it with regular slide. Just make it bigger. That's it. That should be fine.
That's good.
That's perfect, I guess. So, okay. I think I will, do the initial part. Right, so it still needs to be done, even though we're not many of us here.
Yeah. I'm just assuming that there's 2,000 more people on the other side of the camera,
exactly. So. Yeah, so I will, hello people from internet. So we're here today at the Princeton and the PrincetonJUG user group. Today we have a pretty awesome speaker about VoltDB and how it's related to Java, and we're very exciting. And Sita, he's gonna introduce himself and he talk about what he's doing and why this stuff matters and why you should care. And yeah, the link to this video will be available on the on our meetup page. Don't forget, we returning to regular schedule every month. We're gonna have awesome speaker in the heart of Princeton, Nassau Street, Tiger Labs. Thanks them for supporting. Thanks VoltDB for providing us food today. Thanks Hazelcast for supporting all this like online translation, online broadcast and stuff. So without further ado, I'm passing the microphone to Sita, and I will be monitoring the translation. I will be monitoring broadcast. If you can actually ask questions online, and I will ask Sita with this question. So.
Thank you, Vic. Thanks, everyone. Hi, my name is Sita Somagani, and I work for VoltDB. So I've started working at VoltDB about 15 months ago. Before that, I was mainly a Java consultant working for a company called NexaWeb, where we had a platform that lets you declaratively build UI, rich UI. So it was Adobe Flex before Adobe. So I had experience working in different industries, but mostly working on the middleware and the front-end side of things, and in Java. VoltDB was the first database company that I worked for, so it was new for me, and I had to do a lot of learning to both into databases, the more complex databases that we have around these days, the complex decisions that everyone has to consider while choosing their database, and the distributed nature that's becoming inherent in databases these days. So I'm here to talk about VoltDB, the company that I work for, and I think it's a pretty cool technology, and explain you guys the rationale for why VoltDB was built, what kind of applications it is suited for, and also walk you through a small example that shows some of the good features, some of the features that make VoltDB unique. So I titled this an almost boring database because there's not a lot of new concepts that you have to learn here. Pretty much VoltDB is just like any other database that you know, but except it enables your applications to handle fast data without having to say use Storm or Spark or a bunch of crazy other technologies that you hear in the Hadoop ecosystem. So I'd like to get started with the overview of the company. So this company was started by Dr. Michael Stonebreaker. If you don't know who he is, he's a 2014 Turing Award winner, considered father of databases by some. He has built Postgres, Ingress, Vertica, which is probably made him a lot more money than the others. So VoltDB was spun out of Vertica because while working at Vertica, Dr. Stonebreaker saw the need for having a fast database, a database that can ingest fast data, and while being transactional and being able to operationalize the insights that a data warehouse like Vertica generates. So he started VoltDB in 2009. Our first product came out a couple of years after, and we are currently on the version 7 right now. So the big innovation about VoltDB when Dr. Stonebreaker created it was it's in-memory database. It's 100% in memory, and the product was built to run from scratch. It was built from scratch to run in memory. So it does not have the operational overhead of locking or latching or having to maintain concurrent connections that you would see in a traditional database. And being the database for the newer kind of applications, it's a scale out, runs on virtualized environments, so you can run it without any crazy hardware requirements, run it on virtual machines, Docker. It uses a shared nothing architecture, so there is no single point of failure, and it makes it easy for you to use by providing you the integrations with the other players, the other technology in your data pipeline like Hadoop or messaging queues or even other JDBC databases. So it's both available open source and commercial. So the open source version you can download you can clone the Git repository and get started. You can just start using it. Only it doesn't come with the durability and some of the other commercial features like cross data center replication, but it works as good as the commercial version. So the benchmark that VoltDB set was at 2.4 million transactions per second. This was a couple of years ago, I think 2014. I think other databases might do this even faster now, and Volt also does this even faster. But Volt can handle millions of transactions per second, but what really sets Volt apart is your data is never not consistent. Your data is never wrong. You are always working with correct data. So Jepsen, if you're not familiar with Jepsen, so Jepsen testing is just one guy, Kyle Kingsbury. What he does is he takes distributed systems like Aerospike, MongoDB, MySQL, MariaDB. He takes distributed systems and he looks at the promises that these distributed systems make, and he tries to break those systems to see how they fare against their own promises. And his testing is so severe that none of the distributed systems that he tested ever passed, including Volt. So Volt had two issues in the version 6.3 that he tested, but we fixed those in 6.4. And we have included Jepsen testing as part of our automated testing. So this is the reason I highlight Jepsen is Volt promises the highest levels of consistency that any of the technologies that he tested promises, and Volt actually satisfies them. So it's not just about fast data. You have fast data, but it's transactional and it's always correct. Not to do name dropping here, I have some logos here that show the different use cases that Volt has been put into use for. So King.com is the maker of the popular Candy Crush game. They use Volt to ingest close to 900,000 events per second from different games and perform personalization upon those events for each individual players. And we have customers in the financial sector, financial services sector, where they are using Volt to ensure that they are meeting their SLAs for their trades. Companies like HP and OpenIT and Nokia, which are probably used by all the top tier CSPs in the US, these guys use Volt. They find Volt really useful to move from a traditional disk-based, expensive specialty hardware requiring databases to a more commodity databases that can run on a commodity server and database that can scale and that can still handle millions of transactions per second and take the decisions that those guys need to take, those guys in the telecom industry need to take. And CGI and Mitsubishi Electric, those guys are using Volt to ingest events from smart meters in UK and Japan respectively. So Volt's used in many different use cases, and our customers have had success with Volt because of these unique features. So that's why I wanted to highlight these our customer list here. So when we look at the product, the VoltDB as a product, it's easier to explain where Volt fits and what Volt does when we look at the world of data, when we characterize it by its speed. If we characterize data as either being fast in motion or as being big and at rest, then VoltDB solves the problem of the data which is fast and which is in motion. When you need to perform analytics, when you need to perform recommendation matrices, when you need to perform reporting, you need to do derive business intelligence and run machine learning algorithms. Those are the kind of operations you would do on a big data that is at rest. The intelligence you gather from it is might take longer, might take hours, minutes, days. But when you are dealing with fast data, you would need to have analytics which are running on the streaming events, and you need to be able to make decisions on those streaming events. So Dr. Stonebreaker's idea was, when you have fast streaming data and you are able to collect them in big data and you are able to generate insights out of them, you are missing the value of the data if you are not able to take those decisions in time. Say you are a phone company and your user is going to run out of his data in a couple of minutes or in a couple of GB, and the right moment to make an offer to the user might pass if you rely on having all this data being sent to the backend and then alerts being generated later on. You need to be able to take the decisions in real time while being able to use the insights that were generated on your big data side. So VoltDB fits into the problem solving on the fast data side. So how does VoltDB achieve this? So VoltDB, if I have to use 3 words to describe it, it is fast, it is scalable, and it is transactional. So it is fast and scalable. So for these 2 properties, how VoltDB is designed, the choices that were made when VoltDB was designed, they explain why VoltDB is fast and scalable. So at the core of VoltDB is partitioning. So you would partition your data. Say you have 12 cores on your CPU, and if you allocate, say, 9 cores to VoltDB, you would have your data split among 9 different partitions. And each partition would have its own thread accessing that data and making transactions against just that data. So what this gives is you're able to make the best use of your hardware, make the best use of the cores that are available to you, while you are not dealing with the overhead of having multiple threads trying to access different parts of the data. So you are partitioning the data, and then you are partitioning the computation also with the data. So the data and the computation, they live together, so there is very minimal overhead in performing your transactions.
You're not necessarily supposed to watch the camera, so but talk to us, it will be more later.
All right.
Relax.
So it's not 2,000 people on the other side then. Okay.
It's just 1,000,
So each server has its own management layer that it uses for accessing the network, communication between the nodes and stuff. But essentially, the partitions, each partition is its own thread. It controls its own data. So the thread is trying to access the data. You have an operation. It has a little queue. All the operations, the transactions are entered into the queue and are satisfied on the other end of the queue. So this is a serializable isolation that's provided by Volt.
How many partitions by default, or is it like dynamic number?
It's not dynamic. It depends on the number of cores you have on your server. So we would recommend like a 3/4 the number of cores for your partitions, so that you have the rest left for the other network and operating system and the other stuff. So when we are partitioning across a cluster with many servers, you are probably you're probably adding more throughput, you're adding more memory, and you're also could be adding more availability by adding more replicas. So the VoltDB provides high availability by default out of the box. So you can have, say, more than 1 copies of your data spread out among the different nodes in the cluster, so that when one node goes down, you still have the others, the database still up and running. So the data is still going to be correct. There is not going to be any outdated reads or any bad writes on the data, because the replication between the nodes, between the two partitions, is synchronous. So only when both the copies of your data are updated, then the client knows that yes, this has succeeded. So you're not, even though you are adding more replicas, you're not introducing any kind of eventual consistency with the data. It's always accurate because it's replicated synchronously. When you are working with the database as a whole, when from your client, it looks like it's one single database. You can add more nodes. You can have nodes die and then have them rejoined. So it provides a simple interface for the developers. So the data partitioning is something simple, like if you have a table called subscribers and you partition by the subscriber ID, based on the ID, VoltDB decides which partition it should go to. And when you are querying or even writing by the subscriber ID, the client is going to send the transaction to the appropriate partition. So subscriber ID 123 goes to partition A and not to partition B or C. So that's how you achieve the parallel processing. And for multi-partition queries, where you don't have the partition ID, there the query is sent to all the partitions, and then the results are aggregated and then sent back to the client. So the client doesn't know if it's a multi-partition or a single partition query, provides that interface.
What is happening? Is it happening on a particular node that will be taken like randomly maybe, or it happens on the client?
So these happen on the server. So one of the nodes will elect itself as the multi-partition coordinator.
Okay.
And when you have replicas, there would be, if you have say, 2 copies of the data, one of the copies will serve as the leader and the other will be as the slave.
So you can serve it even from backups, basically, right? From replicas, not only from primary partitions,
Yeah.
but also from replicas.
Yeah. So when say one node goes down, if that node contained the master, you can still, the slave will become the new master.
Okay. But for like master slave, do you have a slide for master slave architecture? How it works? Like how you elect master?
So it's a shared nothing architecture. These masters and slaves are elected on the fly. So we go round robin between all the servers and assign, okay, for this partition you're the master, this partition you're the master, and so on and so forth. So it's done by Zookeeper. Just the assigning of the initial coordination so that all the servers start up. But later on, everything else is done by Volt, so that when it comes to processing the transactions, we're not depending on Zookeeper. Zookeeper is just for the nodes to be set up, and add more, take out some nodes in the middle, things like that.
So basically, it's very similar to Cassandra, right?
Yes. Yeah, we have, but we don't. Cassandra is eventually consistent between the nodes, but VoltDB is not. So if you have, say, a replication factor of 1, you have 1 copy of your data, or 2 copies of your data. When you update any 1 copy, you are not going to get back a result unless the other copy is also done updating.
Okay.
So the database, it's always 100% ACID compliant.
Okay, but do you support like more like easing of consistency guarantees? For example, like have a synchronous backup or a synchronous replica, something like that.
So we do have just one tiny bit that you can adjust, but it's within the architecture to always have consistent state. So some applications might not need that, and some applications, they might just be fine with eventual consistency.
Right.
That's not what what we would consider as the ideal applications,
Okay.
for Volt. So as I highlighted in the previous, our customers, we have a lot of customers from telecommunication and financial services, and those guys cannot have eventual consistency. So it's easy to use. because it provides SQL 92 support, and along with the geospatial and some custom functions to work with datetime and being able to use JSON columns that you can search within and also index on. So it's transactional by using Java plus SQL stored procedures. So you can have SQL statements that access the tables, but have the logic in your Java stored procedure. So this enables you to have complex event processing, say, on each of your transactions. So each transaction is, since it executes from beginning to end or not at all, you would put all of your logic inside the stored procedure where you're using combination of SQL plus Java, and your client is constantly sending these events and making these stored procedure calls so that the processing happens at a per event level. I think I'll be able to explain this better when we go into the code a little bit. And in addition, so I think I gave a a high-level overview of how VoltDB is fast. It avoids the overhead of locking and latching, and being able to handle concurrent requests. It's fast. It's scalable because it uses a shared nothing architecture. It's transactional because the transactions are controlled on the server. The client does not control the transactions. So a transaction executes on the server, and they execute one after the other in a serial manner. In addition to that, VoltDB provides materialized views, which is a great feature when you want to derive runtime analytics. You could derive views, you could define views on your tables, on a combination of tables, say to perform summations or aggregations. I will show an example of this in the code example later on. But this is something that's very useful when you would want to have a real-time overview of what's going on. You would want to have maybe like a window of time on which you want to have some summation, have some aggregation, and being able to take your decisions based on it. So these are very critical for applications like fraud detection or distributed denial of service attacks. We do have customers in Japan called Sakura Internet, and those guys use Volt specifically to be able to identify and isolate DDoS attacks. So materialized views is a great way for them to understand that. And the last thing is to have the integration with the ecosystem so that you can drop in Volt as part of your data pipeline. Your data pipeline could be you have Kafka or RabbitMQ messages streaming in, and you have a big data, say Hadoop or Cassandra on your backend where you are running some longer run queries, or you have your JDBC database that serves as your master source of record. So VoltDB provides integration for all those. Kafka or Kafka importer is our first class importer, which enables you to import from Kafka topics directly into Volt because the importer runs on the server within the database itself. So there is no single point of failure, or there is no bottleneck between Kafka and VoltDB. So a lot of our customers, they depend almost exclusively on Kafka to bring the events to Volt, and also being able to write the events out from Volt into Kafka. So you're able to take your decisions in real time. You're able to gather real-time analytics and take the decisions on it, and you're able to do that in transactional manner and at millions of transactions per second. So all of this you're able to do with Volt, and keeping that being able to integrate with the common technologies, you can take advantage of your data at the right time before it expires. You can make advantage of your data by getting the most benefit from it, because you are never looking at older data, you are never looking at stale data or incorrect results. And then you can forward the data on to its next level of layer of processing, say big data or Hadoop. So that's basically the advantage that Volt provides. Any questions?
I have a question in terms of when we talk about Virtualized view, I wanted to ask like if you support like joins.
Yes.
So like, how does it work in terms of performance or like denormalization scheme, or I need to, can you talk, or maybe you have an example already that you can talk about?
Yep. So quickly, we recently added support for joins in materialized views. But when we are talking about joins, there is essentially one big thing that we have to talk about, which is you cannot join between partitions, right? You
So
run
you
your
can
queries.
join, but in this case, you need to have some sort of correlation in terms of partition keys.
Yes, either that, or you can have a table replicated across the partitions.
Okay. So how are you doing this? You have some sort of composite key that you use to define partition key, so two tables with data will end up on the same partition, so you can do join?
So you can identify any one column in your table. It must be a column in the table to be the partitioning key.
Yes, of course, yeah.
And if on the other table also it has the same column, either it exists by itself, or you combine different columns to make the partition key, you partition the other table also on the same column, the hash is going to reach the same partition. So you can join the other one is you partition. Okay, so I have a small example here of a Volt application. So this is part of our open source distribution. This is Volt. So I have two packages here. One is client, the other is procedures under my MetroCard application. So both are Java, all are Java classes. So the client, what it does is, this essentially has the most code. It uses the VoltDB's client object and makes requests to the server, makes requests to the database to say, so this is a MetroCard application, create me so many MetroCards, and then simulate a number of swipes. So simulate so many swipes per second, so many swipes per minute. So that's the functionality of the client. The client uses the client object and makes the request to the database and has all the logic to generate these random, these random numbers for these requests. On the server, I would just want to show just one of these stored procedures. So on the server, we have stored procedures. These are the transactions that would be running on the server. So the card swipe, so I just want to show just one of these stored procedures. The swipe is a transaction. The swipe involves, let's check if the card is correct. Let's make sure the card has enough fare when leaving out of the station. Let's make sure we put a charge on this card, and also notify the customer if he doesn't have enough money in that card. So this whole transaction is written as one stored procedure class. So in this stored procedure, you can see the SQL statements that do the actual work and the Java code that invokes these SQL statements to reach its goal. So the schema is defined in SQL as in any other relational database. So here we have a replicated table called stations, which has the name of the station, ID, and fare, and then we have partition tables. So the replicated tables are the ones that are going to be replicated across all partitions. So if we had, say, 28 partitions, this table will be in all 28 of those partitions. So these tables are good for data that doesn't change that often, and you would want to join with these tables. The partition tables are the more fast ones, the ones that are being changed, that are being updated a lot. So we have the cards because we are creating new cards, or we are accessing the cards whenever there is a swipe. And we have the activity table, which captures the activity that is recorded by each card at each station. So these are the two partition tables. We have the cards and the activity, and both of these tables are partitioned on the card ID column. And what this enables us is we can join between the cards and the activity tables. And the way VoltDB does export is by creating this concept called a stream. You can create a stream which has the semantics of a table, only there is no actual table being used here, only no actual table being created here. This is just Hadoop messaging queue, whatever the technology might be. If it's supported by Volt, you can create a stream and you can insert data into the stream as if it were a table, and the data is going to go out and be pushed out to the external system. So this stream I have here, this export stream is for say sending notifications out. If a card is below balance, or if it's close to a certain amount within its going below balance, then I need to send a notification to the user. So this would be something that would be generated transactionally whenever the user swipes the card. We make sure if this trigger is matched, and then we send the export notification
so
out.
it's like a listener or something like that, right? So some event happened, and this event will be recorded on the stream.
So we explicitly insert into the stream.
Mm-hmm.
So in the card swipe, if the card has insufficient balance, right, this is where we say, well, run this SQL.
Mm-hmm.
This SQL is basically insert into this table.
Mm-hmm.
So when I do this, whenever this SQL statement is invoked, we are pushing this out onto a queue that is dedicated for pushing this data out to the downstream system.
Can you show this definition once again, how you define which table to listen?
This one?
Okay, so partitional and target. So where are you defining which table to listen?
It's not listening to a table. We explicitly write to it.
Oh, okay.
So
you're writing to the string. Okay.
Yeah.
And because it has semantics of table, it looks like a regular insert.
Yep.
Okay. But it doesn't buffer. There should be someone on the other side to consume it, right? So there's no durability on the stream. So you wrote the stream. So or it's
there
like
is a buffer.
Queue or topic semantic. What kind of semantic stream has?
It's at least once guarantee.
Uh-huh.
So there is a buffer, and if the downstream system is not able to catch up, then these messages will be written to the disk. So this buffer will be written to the disk, so that when the message, when it's able to write the messages out again, it's going to read from the disk and then push those out to the downstream system.
Makes sense. And in this case, can you define durability of this? I mean, say evict after 2 hours. Otherwise, just in 2 hours, we're not going to be interested in this one.
We can define that durability as part of the table definition itself.
Okay.
We can say, well, based on this clause, delete the rows.
Right.
So that's for the actual tables. So the materialized views, which are the more interesting concept, is something that we define here with the create view. So in create view, here I'm defining a materialized view that is joining the activity and stations so that it gives me the activity at each station at each second. So let me run this. Okay, I have the server running.
Can you make font bigger?
Yep. All right, let me start over then.
So what's the difference between Community Edition and Enterprise Edition?
The Enterprise Edition provides durability to disk. Community does not. So if you want to capture a snapshot, you will only the Enterprise Edition lets you do that.
Okay. So Enterprise Edition, so Community is in memory only, right?
It's in memory only, yes. And
but you can interface with some other database?
yeah.
Okay.
Yeah, you can pipe your data out to another database and have durability provided that way. And Community Edition also does not come with cross data center replication. So the enterprise version comes with both active-active and active-passive cross data center replication to multiple data centers. Okay, so I'm going to start the server. So VoltDB has command line interface that you can use to start the server, start the whole cluster. The command would simply be VoltDB start and give all the host names separated by a comma, and all the servers are going to wait for each other, and when they have the full quorum, the database starts up. Right now I'm just doing this on a single my local machine, so it's not a cluster.
So what happens, like you have defined a quorum?
Yep.
And what do we know? Like you formed the cluster, everything was fine, and after that, one node went down. So or it's just startup quorum, like the minimum number of nodes that need to start. Can you talk a little bit about the quorum?
Yes. So we provide these variables in a deployment file. So in the deployment file, we specify what's the K factor. If the K factor is 0, you cannot have any node go down. So if you start the cluster with 3 nodes, if one node goes down, your entire database is going to go down.
So it will go down, or it will just not accept any reads or writes?
It will save its state and shut itself down because it's a consistent and partition aware system.
Right. Makes sense.
So if you have a K factor equals 1 and you have a 3 node cluster and one node happens to go down, or if it happens to lose the network connectivity to the others, then these nodes, it's a mesh network, they communicate within each other to try to identify who's the majority and who's the minority. So the majority is going to stay alive and the minority is going to go down.
Is there any way how you can define, say, like read quorum, write quorum? Say, I'm fine with, I will lose availability and drop availability. I would want to be consistent.
No.
Not all features will be available. Okay.
Yeah, it's if your data is crucial and critical and you cannot have automatic decisions made on
But in this
conflicts.
case, like the data is important, but you cannot reach this data because cluster is down.
Yeah.
Okay. That's fine.
So I created, I loaded the SQL. So all the tables use the SQL command to log into my database and access it, so I can see what tables are created, what views are created, and what streams do I have. So all of these are created by running this SQL code, these DDL statements. So I don't think.
Can you make the font bigger? So we still need a bigger font.
Is it okay?
Yeah, that's perfect.
Okay. So we have the tables. It doesn't say which ones are partitioned or replicated, but we can see that with the web console that comes with Volt. So we can see these tables are all partitioned. Try to make this bigger as well. And this is the only table, the stations table is the one that's replicated. So we have preloaded this with some data from a CSV file. So I have 63 stations ready to be used. So I can run the client, which is going to run the benchmark. So it generates 50,000 cards and then fakes these swipes using those 50,000 cards in those 63 stations at random. So we can see, on the management console, how much CPU is being used, what percentage, what's the cluster latency, what are the transactions per second that we're seeing. So this is what's happening on just one single machine. And the number of invocations of, well, we have almost close to over a million invocations of this wipe. And we have so much, over a million activity being logged in the activity table. So you can see, the cluster transactions, it reaches based on, how much CPU is free on my machine. It reaches over 100,000 transactions per second easily. Now it's all the way up to 64,000 transactions per second. So I can run, I can use this materialized view that we created. So the secondly entries by station. So what this is giving is, in each second, what was the activity and how much money did that station make, how much money was swiped in that station. So I can say order by. So now I know, so which station is making the most money, right? So if I want to do this in the last second, where second equals well, so if I want to see in a window what's the maximum in a time window, or who's the best performing in a time window, this can be applied in many different use cases. Here we are doing this for which station collected the most money, but this is useful for, say, gaming applications where you want to know who's the top player right now, so that you can make him the best offer. You can segment them accordingly, and you can make them the offers that are going to work out the best for them. And in a denial of service attack, you can have these real-time analytics that are going to inform your decision that you have to make on a per event basis. So this activity, these analytics can help guide you, say in each transaction. Say if we decided that I don't want to have a single fare, maybe I'll have surge pricing based on the activity at each station. So here I could, instead of just selecting the fare from the constant fare value from the stations, I could say, well, give me the top, give me where this, where this station is, how much is it, how much it's making, and based on that I can add to my fare. So all of that can be done within the transaction at each card swipe. So this gives you the leverage to really use your runtime analytics and take decisions in real time. And there is another view that we did not discuss. So this is the alert summary. So this view was created over the stream. The stream is something that represents the data that is being written out to the downstream system. So that data is not in VoltDB at all, right? It's just events, notifications being sent out to the downstream system. So I can define a view on top of that stream so that I am capturing the summary that I need, even though I'm not holding on to that data. So I can define views on the data that I'm holding, on the data by joining the tables that I have in memory, and also define views on streams whose data that I don't even have, I'm not holding in memory. So these are the views give you the cool tools so that you can have these real-time analytics, and in your stored procedures you can make use of these views and take actual decisions per event. And you can see the the performance. It reached about 66,000, but if you had a 16 node 16 core server, it easily goes to 140 transactions per second. So in short, I think I try to give a high level overview of why VoltDB is fast and it's scalable, and it lets you do this in a correct manner, do your transactions in a correct manner. Any questions?
It's pretty cool. What about like stored procedures? Like what is the Java side of this? How you deploy and how it works?
Sure. So let me open up the run.sh. So first, when you write the stored procedure, let me show a simple one. This was a simple one that we used before we added the capability to do joins on views. To be a stored procedure, you have to extend this class and define a run method which returns a volt table, which is like a result set. And you have to define these SQL statements that you say, well, queue all of these SQL statements and then execute them at once, or execute them one after the other, or queue this SQL statement, execute it based on its results, queue another SQL statement and execute it. So you can have imperative logic within your stored procedure while using SQL for actually accessing the tables. Mm-hmm. And you would take these stored procedures and jar them up, compile them into jars, and to load these stored procedures on the database, you would use the load classes command, and you have the updated catalog. Now you have your newer class definitions. So you could do this while the database is up.
Okay, so you can do like hot reloading of your.
Yes.
Okay. And VoltDB is also Java application, right?
Yes. It is a Java application. It runs on JVM, but the data that's actually stored, it's off the heap. Mm-hmm. So the core execution engine is written in C++. Mm-hmm. The Java is the shell on top.
Okay.
That protects you from the garbage collection and nasty things like that.
Yeah, makes sense.
So yeah, you would load the jar and you would create a stored procedure, say create procedure from class, and give the name of your class, and you will have the stored procedure that you have ready to use. So some of our customers have defined rules engines which dynamically generate these classes, dynamically generate the classes, generate the stored procedures, and make them available to the client. It's a pretty simple example, but I think it covers all the different points. I wish there was a web, cool looking UI to it. But what I have to show for is here. So you have the average throughput, 50,000 transactions per second, latency is 57 milliseconds. Which is, typically not something you can do on a single machine in a relational database.
Do you find that it's better suited to run on clients who run their own servers, or can you implement this in a cloud-based provider?
Yeah, so our customers, more than half of the deployments of Volt are on virtualized environments.
Okay.
Whether they are public or private, most of them are on virtualized.
Okay.
And actually, we've recently put a AMI in the marketplace,
Mhm.
so you can try it out for 30 cents
Okay.
an hour.
So can you talk a little more about like integration with other, or I see like on your website you have a bunch of like use cases where you're replacing some of the like stream processing engines like Storm or Spark.
Yep.
And can you talk a little bit about this one? So why you think this is kind of your approach will replace the Spark approach?
So what we have seen, well, Spark is not really what we are trying to replace, more like Spark streaming. And Spark streaming is micro batch. It's not really real time per event processing. You batch the events into small, tiny batches and process them together, take this snapshot and then process them as one. So that might not work for cases where the events can come out of order, where you absolutely need per event processing, and when the decisions that you have to take are very crucial, and when you have to take them one event at a time, those are the use cases where we have found our customers prefer to use Volt over Spark or Storm. And having co-location of data and computation makes it for a much smaller cluster than what Storm might need when you are accessing data from Hadoop or God knows what.
Okay. How you interface with other languages? So the programming languages, basically.
Yep. So we provide connectors. I think it's in the last slide. So our Java client is our first class client. It has the most features. Our C++ client is next, because most of the telecom companies, they use C++, and you can interface with VoltDB using JDBC or our JSON. JSON is probably not the best performing, but it's easy for you to use, and C# and Python and PHP. And the wire protocol that the server depends on to understand the messages, it's open, so you can implement your own client in any language of your choice. So we have our community contributing a Golang client, and I think maybe a Clojure client, or maybe not.
Clojure is easier, right? Because it's you can grab the Java functionality. Do you have any examples how you work with Java, for example, with Volt?
How we work with Java?
Yeah. Or how Java works with Volt?
So this is the client, right?
Mm-hmm.
So in the client, this here I'm using the Java client. For Java client, I'm importing the VoltDB's Java API.
Okay, but it is not JDBC, so it's like a
Yes.
synchronous driver or maybe synchronous, but
It's
I don't know.
yeah, it's both. You can choose between synchronous or asynchronous, and JDBC only slows things down. That's why we have our own
Exactly, yeah.
client. So if you wanted to use a tool, that uses JDBC, then that's fine. You can run your ad hoc queries, but when you are running your operational systems on Volt, you would want to have it optimized, not worry about the compatibility. So
Right.
we provide.
So basically, you have a Java client plus you have a JDBC driver.
Yes.
Okay.
Yep. So there's a bunch of examples on our GitHub. Go into examples. There's one that shows our geospatial capabilities. So we recently added geospatial primitive functions and data types. So you can represent points, polygons. You can have functions that calculate distance between points, whether a point is inside a polygon or outside, or distance between two polygons, things like that. So there's a bunch of examples that that come with the distribution, but a bunch of examples outside as well. The clients are all available to download for free and use. So we have a Node.js client as well. And connectors to other systems like Teradata, Hadoop, Vertica, Kafka. So it's easy to give VoltDB a try. It doesn't take a lot of time, and it's free.
Do you see it's a replacement just of MySQL type of use cases or Oracle use cases?
It's a good question. So we don't do everything that MySQL does. MySQL has a much richer, I think, SQL capabilities.
Mm-hmm.
And when we are speaking with our customers, what we try to paint the picture where VoltDB can be a fit is you have to basically differentiate between your fast processing and your slower processing.
Mm-hmm.
If you're using your MySQL for your database, period, then your MySQL is not scaling. We have a customer called AirPush. They were using a 100-node cluster, MySQL cluster. That was quickly becoming a pain in the neck to handle. So they had to differentiate between, well, these are the things that we're going to do over time. These are the things that we need to do in time. So once they have made that distinction, they used Volt to reduce their cluster size to just 7 nodes. And VoltDB on 7 nodes does it for them. And for the rest, they're using Hadoop.
Mm-hmm.
So they were able to get off MySQL completely. And same thing goes for Oracle. A lot of our customers have switched from Oracle just because of the high cost,
Mm-hmm.
tremendous cost that they have to pay.
So, just want to discuss once again. So VoltDB is more like for transactional, like OLTP type of use case, right?
Yes.
And running store procs, it's more like an analytical use case that you can solve. Or if you don't want, you do not necessarily need to do that. You can use Hadoop or Spark to do this kind of stuff.
Even the stored procedures are for runtime, real-time OLTP stuff. But you have the you have the capability to generate those analytics, real-time analytics using views. But everything that VoltDB does is for real-time OLTP kind of transactions. So anything else, you can build your own, say, feedback loop. We provide both importers and exporters to other technologies. So you could have, say, Vertica on the back end. Send the now we have the events stream, right, in the example. So every card swipe, you're done with the transaction and you send the event out to, say, Vertica. And in Vertica, you run some machine learning algorithms to ensure that, to say, well, when this user comes up, or this segment of user, make them this offer to recharge. So in Vertica, you have calculated those numbers. And we have a loader, integration from Vertica back into Volt, because Volt also supports JDBC import, right? So you can import from Vertica into Volt and have those parameters in one table, so that next time the event happens, you can join against that table and take the decision. So you can form a feedback loop where you're generating the longer term analytics on your back end, on your big data side, and you're generating your real-time analytics in Volt, and making use of both and taking decision transactionally.
Okay, that makes sense.
So for fraud detection, these things are paramount.
And basically, when you scale any more nodes, you're actually scaling throughput of these operations. Right?
Yes, it's near linear.
Okay, makes sense. No, that's cool.
Yeah, as long as you can, partition your workload, and you have fast throughput, you need fast throughput, I think Volt can, satisfy those requirements.
That's cool. Do you have any questions, or do you have all your questions answered?
Yeah, I can't think of anything right now.
All right. So in this case, thank you very much for your presentation. I don't know if I will be closer to microphone. Thank you very much for your presentation, and hope to see many of you guys online if you're watching this still. Hope you see you next time, March. It's not announced yet, but if you're not here, I will follow our announcement in the webpage. And bye-bye.
Thank you.